Hello, my name is Alexander Couzis, and I'm a professor of chemical engineering at the City College of New York. I've been with the department since 1994. In nature, there is no singular material that exhibits both bulk and surface properties ideal for applications. We often have to modify the bulk properties by forming mixtures, or we have to modify the surface properties by coatings. So, our motivation in the Interfacial Science and Engineering Lab is to find new ways to control the surface properties of materials. And through these new ways of surface control, we want to deliver surface and bulk functionality that is unattainable in readily available materials, deliver surface and bulk functionality to materials that allow its use in new applications, and finally use surfaces and surface templating to direct material growth and synthesis. The applications domain for interfacial science and engineering is actually very, very broad. And in our lab, we have looked at a number of such applications, starting from processes related to separation, processes related to the fabrication and synthesis of nanomaterials, especially particles with unique properties, looking at deterrency, wetting, and adhesion, using materials that we synthesize in the lab for the purposes of additive manufacturing, such as 3D printing, and being able to print both metallic and insulating materials, and eventually evolving these techniques to be able to print things such as batteries by using multiple inks, an ink for the anode, an ink for the cathode, an ink for the electrolyte, and an ink for the separator in one unique step, looking at base processes, which are involved in things like making battery electrodes, and finally understanding the processes at interfacial driven materials and reactions, such as what happens at the interface of a metal anode and the electrolyte, and what controls our ability to generate power out of that corroding anode during the discharge of a battery. In the first example that I've mentioned, we are focusing on batteries that are using the chemistry of the manganese dioxide zinc metal anode. In these cases, I'll focus exclusively on the anode for the purposes of this presentation. We basically have metallic zinc that upon discharge actually corrodes, oxidizes from Zn0 to Zn2+, and the Zn2+ species are actually soluble in the alkaline electrolyte that we use. During charging, these species actually replate onto the anode by accepting 2 electrons, and they form metallic zinc again. These processes, while appear to be very simple, are actually complex in the sense that we do not know what intermediate species adsorb on the metallic surface. We also do not know what the rate limiting steps for these processes are. And at the same time, on the actual anode, there are other competing reactions, such as the electrolysis of water that generates actual hydrogen during this process. And so, in order for us to be able to increase the efficiency of the battery, we need to minimize the parasitic reactions, the electrolysis of water, while figuring out how to overcome kinetic or mass transport limitations during the charge and discharge of the zinc anode during the battery operation. If one were to focus on the particulate nature of the zinc anode, one will understand that the zinc particles, as they undergo corrosion, actually only their surfaces corrode. And very much as a core shell model, the oxide surface increases in size and eventually dissolves in the electrolyte. The metallic particle begins to decrease in size, and the biggest problem that one runs into these kind of situations is that the particle-particle contacts begin to diminish or uh, or are completely eliminated, and so the actual conductive pathways for electrons to allow for the corrosion process to occur are eliminated, and there is no conductivity pathway to the actual interface between the zinc and the electrolyte. How do we compensate for that is by using either compressive forces to keep the particles always in contact with one another, by the stack pressure that is applied into the actual battery, or by using binders that allow the material to stay together. However, these are not efficient, and they actually provide other problems. Our motivation, thus, for this field is to actually build inks or materials that are representative of anodes or of the cathode material, or even the electrolyte and the actual separator, and use 3D printing to allow us to print architectures of batteries where we've maximized the area to volume ratio so we can increase the power generation during the discharge of these batteries, and at the same time mitigate any type of transport problems that occur during the operation of these batteries. Furthermore, this allows for a much easier way to build batteries in unconventional environments. Another area of interest in my research lab deals with the templating synthesis of materials and looking at different templating mechanisms. Specifically, we're interested in being able to use soft templates, such as liposomes or vesicles, where we can introduce these organic self-assembled structures to inorganic materials and synthesize using these organic layers as a template. Such a particular example allows us to use a transcriptive synthesis where the vesicular or liposomal structure is used as a template to grow on the outside of that surface a very thin layer of a metal oxide, such as silica, and so we can generate hollow spheres. By controlling the porosity of the shell, we can now have a scalable way of synthesizing hollow silica particles or other metal oxides, and we can control the exchange rate between the inner and outer domains by controlling the number density of the pores and the size of these pores. These pores again are templated by the presence of polymer chains that are incorporated in the actual vesicle wall. Once these particles are formed, they can be actually assembled through a colloidal assembly process into thin films and forming colloidal crystals, or basically colloidal membranes. And the porosity through these membranes is actually controlled by the pore size of each one of these particles that allows the diffusion or the permeation of a gas or of another species of preference through that material. Furthermore, we can functionalize the surfaces and the actual pore surface in such a way that we can also chromatographically separate out materials as they permeate through these colloidal crystal assemblies. Another approach where we can utilize wetting phenomena or selective interfacial interactions between a liquid or two liquids and a solid substrate is for the separation of oil and water using meshes that have antagonistic wetting properties. So, for example, if we have a mesh that is actually wettable by, let's say, a water phase, but not wettable by an oil phase, then by utilizing this approach where only the water droplets are going to be able to move through the mesh pore while the oil droplets will be captured, one is able to phase separate water from oil quite efficiently. Furthermore, the porosity, the wettability of these surfaces is determined really by the microstructure on the metallic substrates or the actual substrates of the separator. So controlling that microstructure allows us to have surfaces that are either wettable by water or wettable by oil. The final project that we are very interested in the lab deals with particle adsorption on surfaces, and one can very easily understand these type of interactions that occur when a particle approaches a substrate. Whether it will adsorb or not on that substrate determines on the specific interaction of the particle with the actual substrate. It will also be determined by the particle-particle interactions as well as the particle-solvent interactions and the strength of the solvent-solvent interactions. This set of 4 interactions pretty much determines the extent of adsorption of a particle onto a substrate. As part of designing functional materials through these templated approaches, we've also developed techniques in our laboratory where we can not only form hollow shells, but we can also form core shell particles where there is a core functionality, typically a metal in our cases, that is coated with a particular shell. And then these particles can be assembled onto substrates using approaches where we tailor those 4 interactions mentioned. Specifically, the material that we have been looking at in the lab is a silver core that is a conductor and can be used either as a catalyst or as a herbicide or a bactericide. We're using a silica insulator shell that also can be a titanium shell. It could be also a zirconia shell. And the combination of the two actually allows us to generate a metal dielectric composite. We can use these metal core dielectric shell materials or particles to actually form thin layers of very high dielectric constant materials for the purposes of generating or fabricating high efficiency capacitors. The presence of the metal core in these particles allows for a very high polarization at the metal dielectric interface that increases dielectric constant. And because the dielectric shell prevents the actual percolation between the metal cores, we end up with materials that have very high dielectric constant. So one can think of these cases where we are building, in essence, peanut M&Ms, the peanut being our metal core, the chocolate being our dielectric material, and the color of the actual candy is the surface modification that we functionalize each particle with. The ability to functionalize each particle allows us for a very straightforward way of actually arraying these particles onto a substrate using interfacial electrostatic interactions. This is a picture to show you that the process is actually quite robust, and we've been able to scale these particular core shell manufacturing processes. We can have cores and shells in the range of 16.5 nanometers, all the way up to 115 nanometer total diameter of the particle, and we're able to build a large enough. And we've learned how to build large enough quantities of these materials so that we can overlay hundreds of layers of these colloidal particles onto a substrate for the purposes of forming macroscopic capacitors, where we can now measure the performance of the device. I want to thank you for spending time watching this video. And if you have any questions, do not hesitate to reach out to me. My email is written in this slide. You can also Google my name, Alexander Couzis, at the City College of New York. I would be more than happy to discuss with you research opportunities and our interests in the lab. Again, thank you for your interest.